So I'm going to, let's see here. I'm going to talk about, at least the title I gave here is Assessing the North American Multi-Model Ensemble Forecast for Seasonal Forecasting and Decision-Making over Africa. Actually, I'm going to talk mostly about climate services within the context of this. So I'm going to talk a little bit about climate information for society, climate services. We've heard a lot of that today already, services and how information gets transferred. We're going to put this in the context of our work that we've done on African and Latin American flood and drought monitoring and forecast systems that we've installed for UNESCO in a number of locations. And then the context of this is some recent work we've been doing, some very recent work on skill assessments using seasonal forecasts from the NMME system. And so that's basically the basis for doing services, is to be able to provide a skillful forecast. And then I want to loop back and talk about the global framework and whether it's feasible or infeasible, and hopefully give you some things to think about. I'm going to start with this home page from the Global Framework for Climate Services and loop back at the end. The important thing to think here, this is what the home page looks like, and they talk about here, GFCS provides a worldwide mechanism for coordinated actions to enhance the quality, quantity, and application of climate services. So I just want you to think about that a little bit. And this page here. There's a framework that they've actually published, Climate Knowledge for Action, Empowering the Most Vulnerable. And I want you to sort of put that in the back of your mind also. So, two aspects: climate products, the end result of a process for synthesizing climate science and data. These are quotes that come out of this global framework. And then a climate service, which is climate information prepared and delivered to meet the user's needs. And I think it's important in here to think that this is coming down to actual users and not being sent off to another government agency that will go and just announce it. I think of climate services, I've done this, calling this a climate service staircase, from data and knowledge for decision making. And so I've sort of divided this up into colors. Data providers are sort of in the green. Sometime in here in blue is what I call knowledge creators. And then on the top are some clients. And so we tend to exist, and I think, not only myself, but the people in this room, at the green end of this. We do monitoring and forecasts, we use Earth observations, in situ data, models of different types. When we maybe have information services, that is, we take this and we put on a web-based service and some apps to access it. And then someone else might actually take these models and provide some indicators. We've done some drought impact indicators. And then there must be customized products. Maybe they're for someone who does, someone who buys and sells commodities, for example. They may be food commodities, who have customized products, or insurance companies. And then but some of these get integrated with local data, that get integrated with other management data and management decisions. And so as you move up this staircase, climate services value gets created as you move here. And I think it's very important to think that we tend to exist down at the bottom here, you know, the climate people, the hydrologists and meteorologists. But there's a bunch of people at the top who don't really understand what we do at the bottom. And that's the challenge. We've developed our systems around this rather complicated diagram, but think of these as parallel and initially. We've taken climate forcing data, reanalysis, gridded observations, we've downscaled them, we put them into our hydrologic and other impact models, land surface models, and we produce some flood and drought products. Historically, we do it in real-time monitoring, the same things. Instead of taking reanalysis and grid, we've taken remote sensing and global weather models. We've merged all this and done bias correction. And you know, we do flood and drought tracking and real-time monitoring systems. We do short-term forecasting using GFS in through here. We've integrated some of these with some crop models, is what we're beginning to do in impact models, and do 7-day forecasts of floods, and then we do the seasonal work with initially with GFS, that is the climate forecast system from NOAA, and now with the NMME, and again do seasonal forecast. And then we're doing CMIP 5, CMIP 3, CMIP 5, again doing the downscaling, bias corrections, and looking at climate projections. And so this whole thing here is sort of the information generation part until you get down into looking at some of these knowledge creation parts. And so I put this up here on the green, that this is mostly monitoring and forecasting. It's mostly green in here. And so if you go on to our portal, stream.princeton.edu, you come up with this, the African flood and drought system and the Latin American flood and drought system, and you click on this and you go in, and it's in 5 languages. And again, it's just using all of these. And you go into the African one, and you can see, for example, here's it runs in real time, and there's a page here that does all this stuff. This isn't the current website. It should be updated. But we did all this for UNESCO in the hopes of starting to provide a foundation so that extremes can, disasters can, that there can be information to try and have users respond to that. That's the whole purpose of this, is to achieve, water and food security, and be able to do management and dissemination of information. That was a whole challenge that UNESCO asked us to do this, and we did this as our contribution to society. So this, in climate services, this is sort of what happens. Information services, web-based. You have some computers in the beginning, in the center here. You have some data, you have some monitoring, short-term forecasting. It comes in, and this actually runs in my own lab, and then we have regional servers that downscales it and puts it out into the centers in Niamey and Nairobi in Africa, and Santiago in Chile. And then here's an example of what we would call a customized product. This is actually a historical drought over the Horn of Africa, and you have here different products here, SPI3, some soil moisture products, vegetation products of different types down in here, and some stream flow. And you get ensembles of seasonal forecasts. And so this is slightly different depending on the product. You get a different impact exactly what's happening there. But this would be sort of a customized product that would go into the World Food Program, for example, to look about how they would respond to food aid in this area, as an example. And then here's our 7-day forecast from GFS. So I'm going to go back and starting with the next slide and just talk about what we've been doing to try to improve seasonal forecasts. But this here is just the GFS. We use a GFS, and with that, the precipitation comes from satellite precipitation from GPM, from NASA's Global Precipitation Mission. But the rest of the meteorology comes from GFS, and then from that we put that into our models, and we produce soil moisture and stream flow and all of these sorts of things. So let's talk for a few minutes about what we've been trying to do to improve the seasonal forecast. The North American Multi-Model Ensemble project consisted of a phase 1 where they gave monthly forecasts of temperature and precipitation, and now they're moving into phase 2 where they're giving a daily forecast. Both of these are out to 1 year, with a much broader suite of variables. And they've been very slow actually in getting the subseasonal forecasts up. The monthly forecast, which I think were mostly hosted at IRI, so they were fairly easy to get to, and the data sets aren't that large. Currently there's 6 of these. There were some other models initially that dropped out. There was an NMME model, for example, that dropped out. These are 2 Canadian models. This one comes from NASA. In the phase 1, this was the version of the GFDL model that was put in there, and this is an NCAR model that's run at Florida. The subseasonal ones, lots of them, they've only gotten 4 models into the system. There's 2 more that are supposed to go in there. God knows why NOAA, that does this operationally, can't get their daily data between Washington and Boulder, but that's one of the great mysteries of life. So even the NCAR one, which can't even get it from one end of town to the other, can only get about 75% of the data there now. So this is floor. This is we heard something about floor already today, and these are 2 from the Environment Canada. Temperature and precipitation availability. There's some other variables, but we haven't used those. So originally we used a bunch of other ones in here, but let's just talk about this within a climate service system here. So this allows us to go do some data integration and do some SPI and do some temperature anomalies and precipitation anomalies. So this is some recent work that we've been doing. Now, when I first saw this slide, I didn't believe what my postdoc had done. I thought he was coming and showing me results that weren't reasonable. This is on the monthly, so here we have forecast leads, month 0 out to month 5 for the Canadian models and CCS M3, GFDL's old model, NASA's GEOS 5, and CFSV2. So in this column is the equally weighted ensemble mean, and then he's been developing optimally weighted models. And so the one on the right-hand side is the optimally weighted models, and this is the anomaly correlation between these models and our in situ and satellite precipitation and temperature data sets. And so the first thing that you'd think is, how the hell can it be this good on the right-hand side? And after I questioned him strongly, I actually believe that he's doing things correctly. And so, and we'll talk a little bit about how he's doing this optimal weighting, which allows him to have unconstrained weights as long as they sum up to 1. He does take into account correlations among these, so you don't double count like the 2 Canadian models. But he will take results like these negative correlations and says, well, if that model says cold, I know it's going to be warm. And so he builds all that into it. And so this is one interesting result. So that's the equal weighting. Here's the optimal weighting. And then this is for air temperature, and this is for precipitation, which stunned me to the point that I didn't believe he was actually doing it correctly. I mean, if you've done this stuff, you know that you shouldn't get something that good on the right-hand side. But I actually think, after some careful looking at what's happening, that it's actually true that this is actually better than any of these other ones. And so this is brand new work, and so we're continuing to actually make sure that is in fact true. So this is the monthly precipitation, and this is the subseasonal. So the subseasonal, which goes out here 0 weeks down to 12 weeks forecast leads for these different regions. So he does these over the different regions, these anomaly correlations. Turns out the floor gets better with time. Floor is a pretty crummy model in the beginning, and the reason for that is because in this version of floor, they start off from a climatological land initial condition. So they don't optimize the initial conditions, or they don't run it through like a land data simulation system to get good land initial conditions. And so I'm going to have to go talk to Gabe Vecchi to get those results to see what happens. But it turns out that, in fact, this is actually quite stunning that we can actually improve these data sets. And then this is it for seasonal precipitation. This was for air temperature, and this is seasonal precipitation. Still really, really good results when you look at the anomaly correlations up in here. I questioned whether that would be good, and so he did some bootstrapping to actually see at what point does the optimal weighted ones outperform the ensemble means if it's just average, that's the black line, or any of the other ones, and how many years. So he did a bootstrapping over the 32 years of the simulations and looking at the median correlations. And this is sort of performance that he gets. And so this would be, let's say, 15 years randomly sampled from the 32 years, and he does that and he keeps repeating that. And so I think it's in this framework, if you have about ensembles, and some of the centers only do about 15 or 20 years of ensembles, that in fact you can get fairly good results. And this shows that we get consistent results through here. So now here's some examples which I want to share with you when it comes to these extremes. Here's West African drought in the year 2000. These are from the different models. So make sure I get this right here. The ensemble means, the color coding on the ensemble means, that's the red, the green, the blue, and the light blue, fit into the weights that they get in here. In here, you can see that the weights are unconstrained, so they can either be negative or positive. And here's the lead time. And so here's it with these 3 models, and here's the you can see how they range around here. This is the ensemble mean, which has a correlation of essentially 0. This is the value with the weighted ones, and this is the value with the weighted ones, including CCSM, which is an incomplete. And the black lines is the observations. So the dashed lines here is the weighted ensemble means. So one of the things which is quite interesting is that the uncertainties in here are much more consistent than you see when you look at the individual models. Here's an example with an East African drought in 2010, which some of the models said was going to be wet and not dry. And we see that the weighted ensemble means the precipitation anomaly is going to be wet. And you see that with the weighted mean, you get something much more consistent. These years were not used when these weights were developed. So there wasn't overweighting by, when these weights were done, this year was not part of that set of information. And then here's a Brazilian flood in 2011. Same sorts of things. Here's it was going to be dry and floor, in fact. And so these are quite consistent. So we now think that we can get the information that is quite good. And here's for natural hazard. Here's drought and floods. This is basically like a Breyer score, is whether, in fact, if you look at the percentile or the quantile connected to the percentile of 60 percentile, what percentage of the ensembles that you predict when it's weighted will in fact predict that it'll exceed the 60th percentile. And this is the weighted one versus the unweighted one. And so that's where we are in sort of doing this improved seasonal and subseasonal forecasting. Then we have, I'm going to skip through this very quickly, you can just go in there. So we have a whole informatics that go behind all this, where we can get things like precipitation, evaporation, stream flows, and these soil moisture indices. We actually go and take all these, fit them into our seasonal forecast and give stream flows, or we fit them in to a crop models. This is irrigation demand, precipitation minus reference ET, crop forecast, which shows here a forecast out 12 months with different seasonal forecasts. Or this is one for crop yields. This is down in Zambia, where we're doing some work on crop yields and crop forecasts. And so this starts to produce the products that is interesting for management of irrigation or crop yields. And this starts to get up here into indicators integrated with the local data, where decision makers, local farmers, can actually do something with it. So the big challenge is, I'm going to spend just a few minutes at the end. The big challenge is, can we create climate information useful for client decision making? We've talked about the things that's sort of underneath this, but can we actually get up this high up the staircase, or do we sort of collapse out of exhaustion and never make it up there? And that's the important part. So let's go take a look at this picture I had before. I had these two things. This is the front page with vulnerable person, and this framework, which is full of whether we have processes and stuff. But this is what I think is the problem. Here we have the satellite data. The data sort of plugs into the data center along with their system models. Can the information find their way easily to the data center? Well, sometimes yes, sometimes no. But HDF formats and these formats, some people, it's in the data center, but can actually get from the data center to the Climate Product Center? Can the Climate Service Center produce products that are actually useful, can actually get this data? And I know that in GPM, they've been doing a lot of application workshops with very sophisticated people who can't figure out how to use the data, the file formats. And it's much the same with the NMME models. And then what happens to these? Well, gee, there's no other plug because you see nothing, on the vulnerable person. She doesn't have a smartphone and she doesn't know what the hell to do because she's not getting any of the data. It's going to some government data center that may never get out to the people that can actually use the data. And so I think that there's no plug at the other end of this. Some of you have heard of the Group on Earth Observations. This is their portal. This is their portal for data systems. And I plugged in soil moisture and see what would come up. And this is what comes up. Site average gravimetric soil moisture that Alan Betts did someplace and something else. Please tell me how people can use that for a service. I'm just stunned when you look at this. We've tried to do this in Agromet. We've done training in Agromet and APEC and in Cazallac and Santiago. And the goals of trying to provide training and capacity building, but it's really hard. Okay, and in sub-Saharan Africa, there's limited capacity, and there hasn't been much progress in trying to really help the decision makers. It's been a real frustration. In Latin America, where there's better capacity, there's been pretty good progress. When we were down in Ecuador just a few weeks ago and trying to set up improved systems, and we may actually do some stuff in Chile and Peru. But it's a real challenge to go and make that connection there. So in summary and conclusions, we're at the threshold of developing climate services. Most of you know that IBM just paid $2 billion for the data from Weather Corporation. I mean, if IBM's paying $2 billion for that, most of that data is just public data that's been organized. Something's happening. We're part of the European Union's Copernicus Climate Service Program through colleagues in the UK and in Sweden. So this is happening. Our community, we're the data providers and the knowledge creators, but we need to continue our research to make the climate information skillful and make it useful. We don't quite understand how well and what climate products decision makers need. If you ask people, how good do you need it? How fast do you need it? What skill do you need it? I don't think that we know the answers to that. And I would have to say that the data centers have failed to provide easy access to decision makers. I don't think the decision makers know. And I think when they have complicated systems, and they talk about interoperability, they're more concerned about interoperability than they are delivering it. I think there's a challenge there that we in this room should be stepping up to try and do something. And with that, I thank you for your